Let's talk a little bit more about collisions. We have two basic types of collisions, elastic and inelastic. Elastic collisions, the kinetic energy before and after the collision are the same. So that means we could use energy conservation to work through the collision. Unfortunately, a lot of collisions are inelastic, or we're missing some information and we need to use momentum also. So we still use momentum in elastic collisions many times. In elastic collisions, the kinetic energy before and after is different. The perfect example there, two ice skaters standing out on the ice on their ice skates very close together. Neither one of them is moving. Is there any kinetic energy in the system? No. They push off each other. One moves in one direction, the other one moves in the opposite direction. Is there kinetic energy in the system now? Yes, there is. So the system went from no kinetic energy to kinetic energy. Where did that extra energy come from? It was stored in their muscles. It was chemical energy in their muscles, internal to their body, and it was released and became kinetic energy. But we can't account for that. So we can't use energy to get through this. But we can still use momentum. It doesn't matter whether it's elastic or inelastic. Momentum works for both of these. For inelastic collisions, how do we know it's inelastic? Well, if two objects stick together and become one, and there's a special name for that. When objects stick together and become one, it's called perfectly inelastic. So in that case, we know for sure that the collision is inelastic. Anytime you have two objects or more hitting each other, sticking together, and becoming one, we know for certain we're dealing with an inelastic collision. Kinetic energy initial will not be the same as the kinetic energy final because there's deformation, and deformation transforms energy from mechanical energy into heat and sound and other things that we cannot account for. The other way we know it's inelastic, that's one. Another way we know is when one object blows apart, and becomes multiple objects, like a firecracker or a bomb blowing up in midair, or like the ice skaters, two ice skaters holding each other close on the ice, not moving, and then they push off each other and become two independent objects moving. That's one object becoming two objects. We know in that case that we tend to have more kinetic energy afterwards than before because there was stored energy in the system. The ice skaters, it was stored in their muscles and then released, and it became mechanical energy. In the firecracker, it's stored in chemical energy in the gunpowder or whatever's in that firecracker, and when it ignites and releases that energy, it becomes kinetic energy of the parts that fly apart. Elastic collisions. How do we know we're dealing with elastic collisions? Well, there's two ways. We are told it is elastic. That's a surefire way of knowing the collision's elastic. If it's stated in the problem that it's an elastic collision, believe them. That's the surefire way of knowing. The other way is to actually calculate the kinetic energy before and after. Does it equal K final? Calculate the kinetic energy before, calculate the kinetic energy at the end, and see if it's the same before and after the collision. One more note about inelastic collisions. We know it's inelastic if the two objects stick together, become one. We know it's inelastic if one object blows apart and becomes two. But it may be inelastic if the objects bounce off each other. And how do we know? Well, then you come up to elastic and you try those two approaches. Are you told the collision is elastic or inelastic? And if not, then you'd have to do the calculation. And if you're not told and you don't have enough information to find K initial or K final, then you assume it's inelastic. So in essence, you need to use momentum to get through collisions almost every time. Sometimes you get lucky and you can just use energy. But pretty much momentum is our tool for collision problems. One thing students always ask, how do I know which approach to take with the problem? When I'm solving a Chapter 8 problem, I know it's an energy because that's what Chapter 8 deals with. When I'm solving a Chapter 9 problem, I know it's momentum because that's what Chapter 9 deals with. But on the exam, I just see the problem. I don't know which one to use. Well, you have to get used to picking out when these different techniques work. Collisions. And a collision, I'm saying, is one object blowing up and becoming multiple objects banging into each other and sticking together, or multiple objects banging into each other, bouncing off each other, and going their separate ways afterwards, like a pool table, a billiard table. Any of those are collisions, and as soon as you see collision, you should think momentum. So one key that physics instructors like to test students on is to see if they know when to use energy conservation and when to use momentum conservation. And you can do something very simple. You can put together a problem where you need to use both, but they don't both work at the same time. Let me give you an example. Let's say initially I have two objects. I'll make them cart 1 and cart 2. And let's have cart 1 moving this way at, what should we have? 3 meters per second. And let's have cart 2 at rest. And then at the end, what happens? Cart 1 and cart 2 stick together and then roll up an incline. And eventually they come to rest. They roll up that incline and come to rest. And we want to know, how high are they when they come to rest? What do we have going on in this problem? First thing we have going on is a collision. So we should be thinking momentum will get us through that collision. Can we go all the way from the beginning of this problem to the end by just using momentum to solve? No, because momentum only works when the system's isolated. And here we have the force of gravity reaching in and doing work on these carts as they go up the hill, slowing them down. And at the very end of this problem, there's no momentum. We have two carts stuck together up on a hill with no velocity, so there's no momentum at the end. So we can't go from the beginning all the way to the end using momentum conservation. Can we go from the beginning all the way to the end using energy? No, because we have two carts banging into each other, becoming one. We know that we're going to lose some of our mechanical energy into deformation of the system during that process. So how do we approach this problem? Well, we break it up. I always like to do this. I always like to make a little timeline right underneath here, my drawing. I'm going to make a little timeline. And the first time I'm going to put on my timeline is just before the collision. So what's happening just before the collision? I have cart 1 moving this way, 3 meters per second. I have cart 2 at rest. That's my initial condition. That's just before the collision. Then the next time I put on my timeline is just after the collision. I always have those two times, just before and just after, and I know I can use momentum to get through the collision. So afterwards, what do I have? I have two carts stuck together, moving with some speed. I'm going to call this time 1 on my timeline. And I'm going to call this time 2 on my timeline. Time 3 on my timeline is the very end of the problem. I have an inclined plane, I have 2 carts, and I'm going to call that V3 is equal to 0. And this is V2. I'm just going to call this V2, V1 initial, and V2 initial. And how do I get from time 2 to time 3 on my timeline? I use energy. First thing we have to do is find V2. That's the velocity of the 2 carts that are stuck together just after the collision. So I'm going to use momentum because there's a collision involved. The initial momentum is equal to the final momentum. And what are these? This is the momentum at condition 1 and the momentum at time, or I guess time 1, time 2, and time 3 are my 1, 2, and 3. Those are the subscripts that I'm using. That's why I have a 3 on there and a 2 on there. P1 to P2, time 1 to time 2. We're going to call to the right my positive direction. I have M1 V1 initial plus 0. I only have 1 cart moving initially. At the end, it's M1 plus M2 times V2. And I can put in some numbers now. My M's, I'm going to stay with half a kilogram for my 2 masses. Make them equal. And what do I get? A half times 1.5. And this is 1. So positive 1.5, right? To the right. 1.5 meters per second is the speed. Now let's look at our energy to get from 2 to 3. We can't use momentum anymore, but we can use energy now. So we say energy at time 2 on my timeline has to equal the energy at time 3 on my timeline. There's no external forces in terms of work done if we're using gravity as part of our system now. This is an energy conservation problem. And there's no friction or non-conservative forces. So I'm just going to go ahead and say here, initially, all I have is kinetic energy. And at the end, all I have is gravitational potential. 1/2 mv squared has to equal mgh. The mass is the combined mass, and that cancels. V squared over 2g is the height that the object makes it up to. So I can plug in my numbers. 1.5 meters per second over 2 times 9.8. That's my height. And my height turns out to be 0.115 meters. The important part here is to understand when you can use momentum and when you can use energy, and split up your problem into small chunks where you know you can use energy in this chunk and momentum in that chunk, and then solve the problem.